All right, so I had teens asking me to do some series review, especially because I have a feeling that this is going to be something that comes up on the AP for the BC students. Now, I'm going to go ahead and switch this here. Because we're going to be going through several things, we're going to let constants like A be real numbers, because I don't want to have to say that every time. Okay. So we are going to start with geometric series. Geometric series are of the form where they're an infinite series where they have some a, which is a constant, and some r to the n, which means that we have some radius. That's why we use that r, and we'll talk about why it's called a radius later. And there's something that's happening to it. So with the geometric series, if the absolute value of r is less than 1, series will converge. Series will converge. Where does it converge to? A over 1 minus r. Now there's a proof for this. I'm not going to do that proof. All right. Let's do this. And then if absolute value of r is greater than 1, diverges. We can think of this pretty logically by saying if I have 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th, that's going to go off to infinity very quickly. So we know this is going to diverge. All right. Let's do a practice problem. All right. So let's try this problem where we have n equals 0 of negative 3/5 to the n. All right. So a is always going to be your first term. So since n equals 0, it's going to be 1. And then your r is whatever's inside that exponential expression. So in this case, r is equal to negative 3/5. So this is going to equal 1 over 1 minus negative 3/5, which is 1 over 8/5 or 5/8. Sweet. And if we look on a graph, we'll see that this is going to approach that 5/8 mark when we're looking at what that looks like. What happens if n doesn't equal 0? Let's look at an example there. Okay. If n doesn't equal 0, so let's say n equals 2 for, let's do positive 7/9 because I'm making stuff up as I go. All right, this is less than 1, so we can perform geometric, so it should be 7/9 squared 49/81 over 1 minus 7/9. So we have 49/81 over 2/9 times 9 over 2 times 9 over 2. We should end up with 49/18 after we do some algebraic canceling. Cool. Geometric are very straightforward. We want to make sure we understand these because geometric series come up when we look at power series again. The difference in thickness was bothering me, so I switched back. But the divergence theorem is one of the more powerful and useful theorems we have, just as far as a quick check. And it can prevent us from doing a lot of extra work. So if the limit as n approaches infinity of an does not equal 0 or does not exist, we can determine that our sum diverges. Now, Can we conclude anything else from this? No, because this is the divergence theorem. It tells us if it diverges or it tells us nothing. So I want to try a practice problem. Let's look at a practice problem. All right, we have a practice problem here. Now I'm going to take the limit as n goes to infinity of n minus 1 over n plus 1. Now, let's say n is 100. I will have 99 over 101. That is getting very, very close to 1. I can also look at the coefficients on our highest degree. So our limit's going to equal 1. Since this doesn't equal 0, this diverges. Super useful, super simple, and straightforward. If only life was like that. We can't guarantee this all the time. So let's look at a few more tests. All right, so the ratio test is a very useful thing that we have. So we have some set up here. It also comes up a lot when we get into the power series stuff. So make sure you understand the ratio test divorced from the power series before you bring them back together. Now, we're going to define this limit as n goes to infinity of the absolute value. So this takes care of any alternating things we might have. A sub n plus 1 over a n. We're going to call that L. If L is greater than 1, if I could write letters, if L is less than 1, we have 3 possibilities. If L is greater than 1, diverges. If L is less than 1, if L is equal to 1, we know nothing. We cannot conclude jack. All right, so let's look at an example of this. Ratio test is really great to use if you have things of exponential form, or if you have terms that are kind of easy to start seeing some relationship with, but we want to make sure we fully understand what's happening. So let's look at a practice problem. All right, so exponentials and factorials are something that often indicate to me that we need to use the ratio test. So I'm going to say that I'm using the ratio test, and then I'm going to start computing limits. Limit as n goes to infinity of, so I'm going to do n plus 1, so I have e, oh my goodness gracious, e to the n plus 1 over n plus 1 factorial, and then I'm going to multiply by the reciprocal because it's the same as dividing. So it's over n factorial over e to the n. Now let's get some canceling going. I have e to the n, and I have e to the n here, so I can cross that out. And then I have n plus 1 factorial, n factorial, so I can cancel out all the factorials there. Let's rewrite that. So I have the limit as n goes to infinity of e over n plus 1. Now, I'm looking at this. E is a number, so this equals 0. 0 is less than 1, so this converges. I'm not going to try and finish writing that in the screen size. All right, ratio test, super powerful. We want to make sure we understand it. Similar to the ratio test, we have the root test, where we're going to have the limit. Oh, that's not what I want. We're going to have the limit as n goes to infinity of the nth root of a sub n. And we'll throw some absolute values on there because this will also work for anything that's alternating. Once we are here, it's going to be the exact same conclusions we can make for the ratio test. So L less than 1, L greater than 1, L equal to 1. We have diverge for greater than 1. So even the conclusions are the same. Converge for less than 1. And nah, bruh, we ain't know nothing about this. So we'll use the root test for similar things we might use the ratio test for. Let's take a look at one of those problems. All right, so we have some wonky handwriting. I apologize, but if we're going to apply the root test, we'll write root. And we'll go ahead and write that limit as n goes to infinity of the nth root of n squared plus 1 over 2n squared plus 1 all to the n. So these guys undo each other, and we're left with the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1. We're looking at the highest powers. We're looking at the coefficients on them. And that's going to tell us that our limit is equal to 1/2. This is less than 1. So what does this do? This converges. Cool. All right, let's take a look at another test. All right, the p-test, the test that makes everyone giggle. We have two situations where p is less than or equal to 1 and p is greater than 1. Now, intuitively, when I have a larger power in the denominator, that means this is getting smaller very quickly. So I can quickly conclude that p's greater than 1 converge because of the opposite thing. So if I have p equals 0, for instance, that is adding 1 infinitely because I have 1 over 1 forever and ever and ever. The trick here is this 1. If I have 1 over n in my series, that is the harmonic series. And that's harmonic. And the harmonic series diverges even though it looks like it should converge. So these guys diverge. The p-test isn't used very often alone. It's usually used within another test, but it's helpful to have that understanding under your belt. Think about how you can keep this around in your head as something intuitive, make some association with it. All right, let's look at some of those other tests. All right, we have a lot of operating assumptions with the direct comparison, but that's just to get it out of the way. We're starting with an. An is the thing that we're trying to find out about. And we have two series, dn and cn. dn is a divergent series, cn is a convergent series. We're also assuming that an has no negative terms, so an is greater than 0 for all n. That's what that says here. All right. If we have it so that if an is less than or equal to cn for all n, an will converge. This is saying, hey, I have something that converges and that's above it. Once we are doing the same thing, so if dn is less than or equal to an for all n, an will diverge. So if I know that something smaller than my thing is diverging, that's going to push everything above that thing to diverge as well. Direct comparison is particularly useful if you already know some stuff about the other series and you can pull that knowledge in. There are a few other ways to compare, and we'll look at the limit comparison later, but let's look at an example problem for this. All right, so you may be looking at this and be like, well, Mr. Woodruff, we just talked about the p-test, and this should converge by the p-test. But the p-test says nothing about having any addition here. So here's what we can do. We can start with this statement. N squared plus 3 is less than n squared. Sorry, 1 over n squared plus 3 is less than n squared. We are in a situation here where, because the p-test, we can say whatever we're comparing to converges. So this can converge by comparison. It's as simple as that. You have to make some relationship between what you're comparing it to, show that that's true. When I first learned this, I would do a few more steps where I would start with n squared is less than n squared plus 3. And then when you flip everything across the reciprocal, or sorry, when you flip everything across the fraction bar, your greater than or less than symbol, your comparison symbol switches direction. So this is what I used to do in college, is use this setup. Follow your heart, figure out what works for you, figure out how you can use that. And this is specifically using the p-test. We can use any other kind of test that we know of to determine things about stuff we know. I know that sounded very vague, but I promise it has some application. All right, let's look at another test. Okay, so the limit comparison test has a general statement where we can use this, and then I'll get into the more specifics of it. So if the limit as n goes to infinity of an over bn equals some c, where c is not infinity and it's not 0. So c is bounded by 0 and infinity, somewhere in there. There's an infinite number of possibilities. Then an and bn do the same thing. Okay, so I could write this, but it's basically saying, okay, so we have a few other statements we can use. If the limit as n goes to infinity of an over bn equals 0 and bn converges, an whoop, 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 whoop. Yep, the sum an converges. Super nifty. If we think about this logically, we can say, hey, bn is converging and it's bigger than an, and that's what's driving this limit to 0. So if it's bigger and converging, that does the same thing as we saw in our direct comparison. Now, I'm running out of space here, so let's look at what happens in another situation. All right. If we have this limit as n goes to infinity of an over bn equals infinity, and bn diverges, sorry, then an will also diverge. We can think of it this way. bn is going off toward infinity or doing whatever, and it's still not defeating an. So that means an is bigger than bn. It goes back to that same theory as in the direct comparison. We have all these. Where would this be useful, Mr. Woodruff? Let's look at an example problem. Oh, Mr. Woodruff, that's so gross. What can I compare it to? Well, let's see. I have something that looks kind of like 1 over n. So I'm going to do this. I'm going to take the limit as n goes to infinity, 3n plus 2 over n plus 1 squared. And then I'm dividing by 1 over n, so that's the same as multiplying by the reciprocal, which now gives me the limit as n goes to infinity of 3n squared, and I don't care about the rest, over n squared, and I don't really care about the rest, because I want to look at those highest degree parts of our polynomials. So now my limit's going to equal 3 based on the coefficients. This means it's going to behave the same as this, 1 over n, this diverges, so this means we're going to diverge by the limit comparison. Neat, right? Now, I want to walk through a little bit how I got to the 1 over n. I wanted to look at this and see what I could get it to look like, the simplest form I could get it, how I could simplify it. So I started by canceling out one of those n's because I have an n squared down here, kind of ignoring the coefficient because we can always factor those out of our series. It's all right there for us. All right, let's look at another test. Okay, so alternating series have 3 specific criteria. I can think about a few other ways to write this. We can add n plus 1 and start at n equals 1. It's really up to you as long as there's a negative 1 to some alternating power. Now, the 3 things we need to keep in mind are that I need a pen, 1, a n is greater than 0 for all n. So each part of the term is positive, all those a's. The negative only comes from that negative 1 to the end. It may not be in this form right away. We may need to factor it out, but that is ultimately what we're looking for. All right. The terms decrease. So an decrease as n approaches infinity. If you don't know what decreasing is, let me know. Reach out. It's an important term to know in these contexts. And then the last part, where it's the computation part, we need to know the limit as n goes to infinity, an equals 0. These two should go hand in hand. I haven't necessarily thought of an example of this not being the case, but it happens. All right. We were talking about the harmonic series earlier, and I want to talk about the alternating harmonic series. So let's look at a practice problem. All right. So the first thing we need is when we factor out this negative here, are all the terms positive? Yes. Are all the terms decreasing? Yes. Because 1/2, then 1/3, then 1/4, those are all getting smaller. So 3, we're going to compute that limit. Hey, that equals 0. Great. This is going to converge. This is counterintuitive because I've been shouting at you about how the harmonic series diverges. But when it alternates, it's moving on each side of 0 back and forth, getting closer and closer each step. All right, for this second example, we want to check these things. So 1, are the terms positive? Yep. Are the terms decreasing? So if I plug in 1 here, I have 1. If I plug in 4 here, I have 1/2. If I plug in 9 here, I have 1/3. So they're decreasing. I'm skipping n specifically because I don't know what square root of 2 is. Oh, I do. It's 1.73. But you might not know that, but we know that it's decreasing. So pick n values you're familiar with. So let's take a look here. Take that limit as n goes to infinity of 1 over root n. Now, does this converge or diverge? Or what does this limit equal? We have 1 over infinity square rooted. That's going to equal 0. So yes, this also converges. Sweet. Let's look at another test. Power series are when we start considering the x values that would make this converge and what range of x values we have. So if I am looking at this here, I'm going to use my pen. The limit as n goes to infinity of a n x to the n plus 1 over a n x to the n, a n plus 1, blue, 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 blue. So that means I have a n plus 1 over a n x. There's some relationship here. There's some absolute values where we can set this equal. And if we want it to converge, we want that less than 1. So I can go ahead and solve for x, where absolute value of x is going to be an over an plus 1 because I'm multiplying by reciprocals. And we can associate that there. Let me get a practice problem to show you kind of what we're looking for in terms of looking for a radius of convergence. Hey, I said it. Remember that R that we saw in geometric? You can also think about that here. All right. We are at a point where I have things to the n, so I want to probably use the ratio test to cancel things out. So I'm going to start by doing this. I have the limit as n goes to infinity. I'm going to absolute value of x minus 4 to the n plus 1 over n plus 1 times negative 2 to the n plus 1. And again, I don't have room to write the division, so I'm going to multiply by the reciprocal. So undo, n times negative 2 to the n over x minus 4 to the n. All right, absolute values, let's start canceling things. So this part is canceled. We're going to group these guys. This whole thing is canceled. So this turns into limit as n goes to infinity of x minus 4 over negative 2 times n over n plus 1. Now, n over n plus 1 is n goes to infinity. That's going to go to 1, so we can ignore that. I now have x minus 4 over 2, and I want that less than or equal to 1. So let me go to another page because I don't have space. All right, so this is where we left off. I now have absolute value of x minus 4 is less than 2 because I multiplied both sides by 2. Because there are no n's left, I know that this is what I am equal to, so I actually don't need that. I should have just used an equal sign. All right, we can go ahead and unravel this. So I have negative 2 is not how that works. It is less than x minus 4. It's less than 2. Add 4 to all the places. I have the statement 2 is less than x is less than 6. And then if we divide that in half, or once we get here, we know our radius size is 2, and our interval of convergence is this guy here. So there are different things you might ask. If you're being asked what the radius of convergence is, all you need is this step here. If you're asked for the interval, you need to solve outside of the absolute values. That's the difference between the two. All right, let's look at other stuff. Okay, so with the Taylor and Maclaurin series. Maclaurin series are Taylor series centered at 0, which I have noted here. This is mostly intended as a notes page for you, but I'm going to talk over it a little bit. When n equals 0, it should always start at n equals 0, assuming that you are computing a Taylor series starting from the function itself. That n in parentheses is the nth derivative, and then we have our n factorial that's included in all sorts of proofs about Taylor series, but I'm not going to prove it to you. A is the important part. So A is the part where it's centered. If you are approximating a value of a function, you want to make sure it's centered near that value, because the closer you are to where you're approximating, the better your approximation is going to be. Also, as a note, Taylor series are what your calculators use, but like going on forever to compute things. So think of it that way. This is what your calculator is doing to be as precise as possible. All right, let's go into more details. When you're computing a Taylor polynomial, we have this statement, and I use a table where I have my n, I have my derivative computed, and then I have my derivative evaluated. So this gives me a step to like figure out the derivative in the box and then go plug in numbers. If this doesn't work for you, don't use it. This is also, I think, a Saxon specific thing. I don't know. I like to stay organized, so I'm a fan of tables. Let's see what this actually looks like with one of the functions that you're going to need to know. So let me go pull that up real quick. All right, so once we are here, we're going to approximate we're going to find the Taylor polynomial rather for sine of x at this a equals pi over 2. So let's go ahead and scroll, if it'll let me. Here we are. I don't know why technology is being weird today. All right, we are here. I have filled out a table because I'm hoping that you know your trig derivatives. Sine itself is sine. Sine of pi over 2 is 1. If you don't remember this, go spend some time with your unit circle, please. These will alternate because sine and cosine are cyclical. There is going to be a pattern very quickly. At n equals 4, we can see that pattern starting over because I have sine again here. Now, notice that every other term is 0. That means we're going to have to do something for our Taylor polynomial to deal with that. So I went ahead and pulled those coefficients, I know words, coefficients, plugged them into this formula here to start a polynomial. Our first term is 1. That looks like a minus. I don't really know why it's all funky. And then I have just the even parts I'm noticing. And don't forget to subtract that center. That's telling me, hey, this is about pi over 2, and those factorials. A thing to note, when you're trying to write something as a series from a polynomial, for sine and cosine, your factorial and your exponent expressions should match. If they are not, either there's something happening to the function or you did a derivative wrong. Check yourself, there will be a clear pattern. If you're not finding it, please reach out. All right, let's go on. All right, so this is 2 out of 5 of the series you need to know. So for e to the x, you have 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Da, 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 da. That is super nice and goes into a really beautiful setup here. X to the n over n factorial. Okay, for sine, if it's not centered at pi over 2, it's actually going to be an odd expression. So sine itself is an odd function, and that's how I remember this. Cosine's an even function, but at 0, sine is 0, so we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. The way that we can simplify this is we're starting at n equals 0. I have a negative n, and since my first term is positive, I can go ahead and start at n. Some people do n minus 1. It's up to you. In this case, I'm going to put x to the 2n plus 1. Since when I plug in that 0, I'm still going to get x to the 1. And then my factorial is going to be the same expression, 2n plus 1. Now, there are people who express this with 2n minus 1. You just have to shift everything over, but it's still the same. What I am seeing, I have cosine, which I already said was an even function. So let's go to that expression here. It's going to be, not x cubed, x to the 4th, because we are only dealing with evens. That's minus. I want to make sure that I'm expressing this negative 1 to the n, x to the 2 n over 2n factorial. All right, and the natural log is a little similar to e to the x. I wonder why. They're inverses of each other. So I have x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, blah, 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 blah. This is going to simplify to n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1 factorial, which we can also simplify by starting at n equals 1 to infinity, negative 1 to the n plus 1, because our first term is positive, x to the n over n. No factorials involved. Part of this is because the coefficients from your derivatives cancel out with part of your factorials. All right, let's look at the last Taylor series. This last Taylor series is probably the nicest as far as straightforward things go. It would help if I was writing. I have 1 plus x squared plus x cubed plus all the things, which, hey, that simplifies really easily. N equals 0 to infinity, x to the n. Now, you can manipulate all of these by integrating or taking derivatives to find the integral or derivative expression of whatever function you're trying to deal with. That's the series review. Holler if you have questions.